Awesome. Thanks for the introduction. I'm Ryan Marcus. I'm a postdoc with Tim Kraska. I know some of you might not necessarily know what that means. Being a postdoc is the answer to the question, how can I get 10 years of formal education and still not make any money? So with that being said, I'm very excited to be talking about possible uses of machine learning for query optimization. So the way that I'm going to structure this talk is I'm going to do a little bit of review about what query optimization looks like and how cardinality estimation and cost modeling play into it. And then I'm going to give some background about deep reinforcement learning and machine learning techniques as applied to database systems. And I'm going to talk about one of our state-of-the-art systems called NEO, which we believe represents some very interesting results in the space, but also comes with a lot of practical barriers. So query optimization as a problem is essentially the task of transforming a SQL query, like the one on the right, into an execution plan, into something that the database execution engine will actually execute in order to produce the query's results. So in general, these things are massive efforts. In Postgres, which is the state-of-the-art open source SQL database, there's around 42,000 lines of code just in the optimizer. In SQL Server, which is one of these state-of-the-art commercial systems, there's over 1 million lines of code just for the query optimizer, which is enormous. Oracle, another corporation that makes a state-of-the-art database, wouldn't tell me how many lines of code their query optimizer was, but they did have about 45 to 55 full-time employees working on it. So that translates to about $5 million a year. So query optimizers are extremely complex. People spend a whole lot of money building them. So in addition to these query optimizers being extremely expensive and representing huge both monetary and time investments from both the open source community and the commercial world, they don't work perfectly on their own. The end user generally has to tune the query optimizer in order to get the super awesome best performance out of it. So we did a simple experiment with all of these databases. Depending on the exact system, we were able to get between a 15% and 25% boost from tuning the optimizer on a particular database. So the point I'm trying to make here is that first, the database developers spend a huge amount of time on these query optimizers, and second, end users still have to spend an incredible amount of time on these optimizers to get them to work really well. The reason that query optimization is so difficult is because they contain a lot of different components that interact in surprising ways. So the sort of classical model of a query optimizer consists of 3 components. The first component you have is cardinality estimation. The goal of cardinality estimation is to estimate the size of the intermediary parts of your query. So if you have a query with 8 joins, you would use cardinality estimation to figure out which one of those joins to do first, which ones to do second, which ones to do third, etc., based on their size. The second component, and cardinality estimation is normally done using a variety of methods. You might use simple histograms, and if you use simple histograms, you'll find yourself making a uniformity assumption to deal with correlations between columns, or you might use more advanced techniques like most frequent value lists to try to capture like heavy hitters and outliers inside of your table. The second major component of most modern query optimizers is a cost model. And the goal of a cost model is to take that information from the cardinality estimator and determine how long a particular operator will take. So for example, your cardinality estimator might say, hey, the join of these 2 tables is going to be 10,000 rows. Then it's the job of your cost model to say, okay, well, if it produces 10,000 rows, I think it'll take 8 seconds to run, or something like that. Cost models are normally hand-tuned sort of polynomial heuristics. You might think, okay, the hash join algorithm is linear. The merge join algorithm is linear, but the sort step is n log n, and with sort of tuned coefficients for each one of those pieces. The final part that sort of combines those 2 pieces together is some kind of dynamic programming or DP search method. So because the space of all possible query plans is very, very, very large, you need some kind of solution, some kind of heuristic algorithm or dynamic programming solution to find the optimal space within it. Generally, these sort of search algorithms are NP-hard, like they're solving an NP-hard problem. And so the search algorithms are either exponential, taking a runtime of like 2 to the n or 3 to the n, something like that, or they're not exact, right? And there's some polynomial algorithm that doesn't get the optimal plan, but it runs much faster, like in n squared time. So a few examples of those is Postgres will use a 3 to the n algorithm to find the exhaustive optimal for most queries. Whereas SQLite, a much smaller and simpler database, will use an n-squared quadratic heuristic to not necessarily find the optimum. So the common wisdom in the database community is that the cost model and the search algorithm aren't too tricky. The really, really hard part is cardinality estimation. And the reason cardinality estimation is so difficult is because of correlations. If you have two particular tables that don't exactly map one-to-one completely uniformly, then doing cardinality estimation can be very, very challenging. So just as a reminder for how cardinality estimation impacts a query plan, imagine I'm trying to optimize the SQL query here, just a simple three-way join between A, B, and C. In order to, so here's a join graph representing that. So my choices are, I can do B join A, and then I can do that join C, or I can do A join C, and then join the result with B. So those two options are represented by these two query plans. These are the only possible left deep query plans for this particular join graph. And so a query optimizer would use cardinality estimates and a cost model to try to decide between them. So imagine that I knew the true cardinalities, the actual right answer for both of these intermediate results. So let's say that I knew that A join B is going to produce 8 tuples and A join C is going to produce 15 tuples. Based on that information, a query optimizer would choose the plan on the left because A join B will produce fewer tuples, and then joining the result with C will be a little faster than if you went the other way around. Unfortunately, the common wisdom about cardinality estimation being the hardest part doesn't tell the entire story. So imagine that I had a cardinality estimator, so I no longer have the true cardinalities, but now I have estimates of the cardinalities. And my first estimator gives me these numbers. It says, okay, for A join B, I think you're only going to have 4 tuples. Now this is wrong, right? The correct answer is 8, but our estimator is telling us 4. And our estimator for A join C says you're going to get 9 tuples instead of 15. If we run query optimization using these cardinality estimates, then we have a certain amount of error, right? Our first estimate was off by 4, our second estimate was off by 9. So the L2 error, so to speak, would be 4 squared, the error in the first estimate, plus 6 squared, the error of the second estimate. So even with this error in the cardinality estimation, if I used a query optimization, any query optimizer on these estimates, I'd still pick the correct join plan because A join B is given a lower cardinality than A join C. However, suppose I had another cardinality estimator, and this cardinality estimator estimates A join B to be a size 12 and A join C to be size 11. Now the L2 error is smaller on this estimator, right? The first estimate is only off by 4. It predicted 12 when it should have been 8. And the second estimator is also only off by 4. It predicted 11 instead of 15. However, with these estimates, our query optimizer will choose the wrong plan because A join C is predicted to be smaller than A join B. So cardinality estimation is a very challenging part of query optimization, but it doesn't tell the full story. Just because your cardinality estimates get better doesn't necessarily mean your query plans get better, because what matters is not just the raw size, the raw error of your estimates, but the relative order of your estimates and their relative sizes between each other.
Ryan, I have
yes.
a quick question here. So of course, there is the chance that the proper join order will depend on the next step, right? As well. I mean, we didn't see the cost of joining the result of A with B, joining the 8 tuples with C in the first case and joining the 15 tuples with B.
Yes, so that could potentially, so here I'm using a very simple cost model, which is just the linear sum. So in that case, joining AB with C should produce the same number of tuples as joining AC with B. But yeah, a more sophisticated cost model might care about those other decisions. Here we're just focusing on, did you get the first join right?
Okay.
Yeah.
All right.
But yes, that's absolutely true. This is an incomplete example in the sense that a more sophisticated cost model might choose different things, might go right deep, might do a bunch of other stuff.
Okay.
The point of illustration here is just better cardinality estimates do not always give you better query plans.
That makes sense, yeah.
Thanks for the question, good one. So yeah, here we can see that we have an estimator that gives us a higher error, but it gives us a better plan, which is a counterintuitive result, goes contrary to the traditional wisdom that if we get the cardinality estimation error lower, we'll get better query plans. This might be true on average, but it's not true in the tails, and it's certainly not true in every case. So a natural question that arises from this is, can we somehow use machine learning in order to predict these cardinality estimates, right? Instead of using histograms or most frequent value lists or all these sort of handwritten heuristics that cost $5 million a year, to do these estimates, can we use machine learning models to simply take in a query plan and say, hey, how big will this be, right? Standard supervised learning approach. And the answer is yes, but it has a limited impact on query optimization. So this was a simple experiment that we did using 3 of the current state-of-the-art cardinality estimation learning techniques that we found from the literature. So what you're looking at here is a plot of the relative errors and the relative latencies of these estimators. So that big giant line right there, that bold 1 at the top, that represents Postgres. So if one of these bars hits that 1, that means it's doing exactly the same as Postgres. If the bar is at 0.5, that means it's doing 50% better than Postgres. If the bar is at 1.2, that means it's doing 20% worse than Postgres. So all 3 of these methods, and I'm not going to get into the particulars, it's not super important, all have relative L2 scores, relative errors in their cardinalities, significantly lower than Postgres. For example, the MSCN method has almost 1/10 of the error, almost 10 times less error than Postgres does. But if you look at the actual query plans that are produced and how long they take to execute, it's only like a 2 to 3% improvement. Interestingly, you can actually get much worse. So if you use these other 2 methods, we actually observed a slight decrease in performance compared to Postgres in terms of query latency, even though your cardinality estimates were much better.
So what type of queries you are using here for this experiment?
So these queries are using the join order benchmark, which is a set of queries that have just an outrageous number of joins in them, 18 to 22 joins each in each query. They're really designed to test query optimizers. And the underlying data set is the IMDb movie data set. So some of these queries are asking questions like, show me the actors that were in more action movies than Tom Cruise and have done at least 5 movies with Sony Pictures. So lots of correlations, lots of strange results happening, lots of potential oddities in this data set.
Okay, great, thanks.
So yeah, we can learn cardinality estimates. We can get those L2 scores really, really low using all kinds of sophisticated and fancy machine learning methods. But it doesn't actually really impact query latency. And query latency is the thing we care about, right? That's the thing that I actually want to make smaller. So what we were looking at in our lab is there a way to do end-to-end learning for query optimization? In other words, we don't want to learn to minimize cardinality. What we want to do is we want to learn to minimize latency. And it's a much harder problem, and it requires a little bit of background. So before diving into that, I want to do some background on how the database community and the machine learning community have traditionally interacted and some of the thoughts and theories that have gone behind that. So there's a view in the database community that I think is mostly based on what I call a mythos of deep learning. A lot of people in the database community view deep learning models as black boxes, right? They're just these totally opaque things that you can't look into, that you can't really understand at all, that happen to produce correct answers on your test set, essentially by chance, right? The other view of deep learning is that it's magic, right? Because while yes, it's just a total black box, there's also undeniably awesome results coming out of them. So these images here were created by a GAN, a generative adversarial network. The details aren't important, but none of these images are real images. These were all images conjured by a computer when asked to create a particular class. So for example, the bottom right picture there was when this network was asked, generate a picture of a burger. It's not a real picture of a burger. It's not even close to any other picture of a burger that the system had its input to its training. And it comes up with a pretty realistic looking burger. So we have to reconcile these 2 things of like, oh, it's a black box and it could just totally fail at any time versus these awesome, crazy results that we're getting that are almost magic. And the way that we've been doing that so far has not been super great. So there's been a lot of recent work in applying machine learning to query optimization. Some work by ourselves in terms of using reinforcement learning, and a lot of works based on cardinality estimation in other areas. All of these works including works from me, can sort of be characterized as like a just add deep learning and stir approach. These were really works that were thinking like, yeah, neural networks are magic, they're black boxes, we're just going to train them and things are going to be awesome. In general, these things were characterized by what I've started to call the 5 deadly sins of ML for databases. They used fully connected neural networks. They had leakage between their train and their test set. They would use off-the-shelf reinforcement learning algorithms or regression loss functions like L2 loss. They would have little to no integration with a broader database in a sense, like they wouldn't tell you how to do training or how to deal with data shift or anything like that. And they very rarely evaluate actual query performance, which is quite troubling. And there's tons and tons of examples of this, my own work included. I'm absolutely guilty of this.
Ryan, a quick interruption again, sorry. I think Hassel has a very good question. Hassel, do you want to say it actually?
Hey, so it seems like cardinality estimation for query optimization is like minimizing the regret over all the sequential steps instead of just doing it one step after another. That seems to be the biggest challenge with the approach. So I was wondering if approaches like multi-arm bandits is something that has been looked at in this regard, because they are used for like minimizing regret over multiple steps. I mean, reinforcement learning has been looked at, like you said. So multi-arm bandit would be very much like a, something that we look at before reinforcement learning, right?
Yeah, that is a really, really good point. For people who may not be aware, there's sort of two large classes of machine learning techniques that have been used within the database literature up to now. The first is supervised learning. And supervised learning is what you think of when you think of core machine learning. You have a set of data, you have labels for each one of those pieces of data, and you're trying to teach an algorithm, given the data, produce my label. There's another class of machine learning called reinforcement learning. And the general idea behind reinforcement learning is that you're in this sort of multi-step scenario. You're in a scenario where you're going to make one decision, and then you're going to make another decision, and then you're going to make another decision after that. And each one of those are going to impact your total final score. Now, within reinforcement learning, there are just tons and tons of different possibilities. But one of them that is quite simple, or relatively simple and well understood, is this idea of a multi-armed bandit. So multi-armed bandits are basically like every single step you have 10 options, and you're going to choose one of those options. And when you choose that option, you're going to get a particular reward. And then the whole problem is going to start over again. So you get to make each one of these decisions kind of independently, and your goal is to explore which one of your 10 options gives you the best reward, and then exploit that knowledge. So it's absolutely a really awesome technique, and I think it's a really good thought to jump to multi-arm bandit techniques before jumping to fully generalized reinforcement learning. We actually now have a system based on multi-arm bandits for query optimization that I'm going to talk about very, very briefly at the end. But yeah, you were almost an oracle for this talk. First, we're going to talk about the general purpose reinforcement learning, and we're going to talk about how it doesn't exactly work, and then I'm going to talk about how we're using bandits. Yeah.
Okay, thanks.
Yeah. So the first thing that I want to do in this talk is sort of disassemble this mythos. I don't want us to think about neural networks or machine learning techniques as magic, and I definitely don't want us to think about them as black boxes. It turns out when you dive deep into the current networks that exist now, you can see that their designs is really, really far from arbitrary. They're actually very specific designs designed to achieve a very specific goal, and you can see evidence of that. So what I want to look at is the two biggest, in my mind, success stories in deep learning. The first success story is computer vision. Before we had convolutional neural networks, before we had deep learning, computer vision was extremely limited. It was really a giant step forward, the convolutional neural network. And the second big application is natural language processing, or NLP, where deep learning also represented a huge step forward. And now we call both of these things deep learning. We say, oh yeah, we use deep learning for computer vision and we use deep learning for NLP. But if you actually look at how we use deep learning in these two different domains, we use extremely different architectures. When we're doing computer vision, we, in general, there's exceptions, but in general, we use something called a convolutional neural network. The idea behind a convolutional neural network is that you have this little tiny filter thing, this tiny little box, and you slide it across your image, multiplying each time to create a new image. And then you repeat that process a bunch of times, and then at the very end, you do some fully connected layers. On the other hand, if you don't understand the details of it, it's not super important. I'm about to explain it more. On the other hand, for natural language processing, we do something totally different. We do something called, in general, long short-term memory networks, or LSTMs. And these networks are very different. They're recurrent. They take the input from their previous state as input to their next computation, and are, in general, just a totally different beast. So when we say deep learning, we're talking about both of these things, but the networks that we're using for each applications are very, very specific. A natural question is, why do we do that? And if we look at the history of how these things developed, we can see that when we tried to build a neural network to recognize objects and images, what we did is we modeled those neural networks based on the low-level structure used by the actual human eye. That procedure that we talked about, where you take that little grid, that little filter grid, and you slide it across your image and you multiply everything, that's actually very, very close to what we see when we scrape off sort of the top layer of a retinal network from a mouse, and we lay it out under a microscope. We can see that that is the actual process that is going on. So deep learning people call this biologically inspired, right? We looked at how an expert system like the human eye was capable of recognizing objects, and then we replicated that inside of a computer, right? It's the exact same thing in natural language processing. In order to build a neural network to recognize, for example, words in speech, like in spoken words, we modeled the low-level structure that we see happening in the human prefrontal cortex, which is the area of the brain that neuroscientists hypothesize is responsible for translating speech into symbols in your head. So it's not the part of the brain that does like computation or like reasoning exactly, but it is the part of the brain that like goes from sounds to words and symbols in your mind. And when we look at the processes, the chemical reactions that happen in those part of the brain, what you see is this recurrent structure where you get feedback loops over and over and over again through the same sort of chemical process. And so Graves and others looked at that thing and they said, hey, I can model something on a computer to do the exact same thing. And that's how they got this huge success. The moral of the story here is that if you want to build a neural network to perform a certain task, you can't just use some fully connected neural network. It's not going to work super well. What you have to do is you have to model the low-level structure that is being used by some expert system that knows how to perform that problem really, really well. This is known as an inductive bias. Basically, you're structuring your model in some way so that your model is more likely to represent a form that is good at solving the task that you're trying to solve, right? Our eyeballs are extremely bad at recognizing speech, right? Like, it's just not good. At the same time, our prefrontal cortex is very, very bad at processing images. It doesn't have the hardware to do it, right? So you can think of inductive bias as sort of trying to make the hardware, the neural network architecture itself, match the task that you're trying to solve. So as systems researchers, when we hear that for every single application domain, you have to come up with this highly specialized architecture, we hate that, right? We think that's just like the worst thing ever. The whole point behind SQL and behind databases is that you take any data that you have, you model it with our relational model, and it all just works out, right? So as systems people, we might be thinking our natural first response to seeing complex network architectures might be, isn't there something more general? Right? Isn't there some kind of architecture that we can use that can represent any function? And in fact, we know that there is. There's a very famous theoretical result by Hornick and others that showed that fully connected neural networks, if you have at least 3 layers and they're very, very, very wide, can represent absolutely any arbitrary function. Unfortunately, this piece of wisdom, while interesting, right, while very theoretically kind of profound, that all you need is 3 layers in a neural network to approximate any function, isn't actually super useful in practice. And to illustrate this, I want to think about like a classic data science example. Imagine I have a whole bunch of data that is trying to correlate temperature with ice cream sales, right? So if I have the original data shown here, you can see that, okay, temperature is going up, ice cream sales are going up. Makes sense. There's 2 different ways that I could model this function, right? One is with, so here's 2 examples of 2 arbitrary functions, right? Arbitrary function A, it hits every data point almost exactly right, where versus arbitrary function B has a little higher error, right? Now, even though arbitrary function B has some higher error, we intuitively know it's the better function, right? Like we know, okay, yeah, I'm expecting this thing to have a linear relationship, not look like some crazy curve like arbitrary function A. Now, the moral of the story is we don't want an arbitrary function that fits our data. What we want is a generalizable function that fits our data. And the way that you get that generalizable function in machine learning, well, there's a couple different ways to do it. Classically, the way that you did this was with the idea of regularization, right? You penalize your model for becoming too complex, and you try to push yourself down to like a simpler, more compact representation. In deep learning, we don't really do this kind of regularization nearly as much. We might do L0 penalties or L1 penalties or something, but there's no lasso, there's no elastic net, there's none of these really highly regularized models. Basically, all we do with deep learning is we just use stochastic gradient descent. We just take these giant neural networks that are full of tons and tons of weights, and we kind of randomly find the first solution that minimizes a local minimum. So how do we know that that particular function is going to generalize well in the absence of regularization? The way we do it is with inductive bias. One way, the way that we do it in neural networks, is to model it after a biological expert system that generalizes well, right? Another way you can do it, and the more general way to think about it, is that you're constraining the type of function that you can learn based on prior knowledge of the problem at hand, right? So for example, with ice cream sales, if we want a good inductive bias, we might say, okay, I'm really pretty darn sure that this function is monotonic, right? That it's only going to increase with temperature up until a point. Or maybe you're convinced like, oh, it's definitely going to be linear, right? Then if you model your system, if you take a model and you say, okay, model, you must be linear, or model, you must be monotonic, you're much more likely to get the right functional fit for the domain that you're looking at. So bit of a pop quiz, and if you're not familiar with what these models are, that's okay. See if you can piece together the answer from the hints that I've given. The MNIST task is a classic machine learning task to identify digits. So the goal is to take tiny little pictures of numbers, like the ones I have on the bottom here, and classify them as a 0 through a 9. So for example, for these images, the correct classification is 5, 0, 4, 1, 9. So what we're going to do is we're going to train 3 different machine learning models: a fully connected neural network, a pretty big one, a convolutional neural network, and then an old school random forest model. So, if you want to shout out your guess, feel free, but otherwise just take a couple seconds and try to think which one of these models is going to perform the best, the second best, and the worst. I'll just give people 10 or 15 seconds to make a decision on that.
You can also write in chat if you guys have any guess, and of course there's no problem in being wrong. So
think of it this way: you have a 33% chance of getting it, of getting the top ranked one. Okay, so turns out if you go and you do this, the convolutional neural network, it was designed for exactly this problem. It can get almost 98% accurate. Surprisingly, random forest, our old school ML model, outperforms the fully connected neural network with a score of 92% to 86%. The reason that the random forest model outperforms the fully connected neural network is because of inductive bias. So if we look at the inductive bias of each one of these models, we know that convolutional neural nets have a very strong inductive bias because it was borrowed directly from actual eyeballs, right? Actual biological visual systems. Random forests also have an inductive bias, and it's a little complex, but intuitively, the inductive bias that a random forest has is known as conditional sparsity. The idea is that if you branch once on a certain pixel, because all of the other pixels around that pixel are highly correlated, you're very unlikely to look at pixels near that one again. Fully connected neural networks, of course, also have an inductive bias. They assign every feature a weight, no matter what, which means that at each stage through the neural network, you're doing a dense matrix multiply. This bias is used towards sensitive or very simple functions of your input. Not very good for image classification, which is not a sensitive task, right? If I give you a picture of a 3 and I tweak 1 pixel, it's still going to be a 3, right? So the moral here is that deep learning is fantastic. Deep learning gives you all of those magical benefits that you were thinking about, but only if you have the right inductive bias. If your inductive bias doesn't match reality, you might perform worse than a classical AI method. You might perform worse than a random guess. So the trick is to think about, for my particular problem, if I want to apply deep learning to it, how do I find the right inductive bias? But yes, if you do that, you can get end-to-end learning, you get awesome automatic feature engineering, you get great generalization. But if you don't get the model architecture right, you're probably just wasting your time. So what about database systems, right? What does any of this machine learning nonsense have to do with the actual task that we want to solve? So the question that we asked in our lab was, okay, if convolutional neural networks are to computer vision, what is the correct model architecture to use in a database system? Now, obviously I don't have like the perfect answer to this question, or I would have beaten Oracle and had $1 million by now, but we do have a basic idea, and that basic idea is called tree convolution. So before I get into the details of that, I want to talk about it in the context of NEO, which is our state-of-the-art, we think, learned query optimizer. This was joint work with a whole bunch of really awesome people. Pari and Hongzi, who are PhD students at MIT, Chi, who is a PhD student at Brandeis University, and Mohammed, Tim, Olga, and Nesame, who are our PIs. So NEO represents an early prototype of what we think a deep learning powered query optimizer might look like. And the high level overview of it is that we do not use any hand-tuned cost models, polynomial or otherwise. We do not do any explicit cardinality estimation whatsoever, and we do not do any kind of exponential search. Prior to NEO, we saw with cardinality estimates that you could replace each component of a query optimizer with a learned system in isolation, but doing that didn't really have a super clear benefit on query latency. We think that NEO is the first system to show that you can have an end-to-end learned query optimizer throughout the whole thing. One of the biggest advantages of NEO is that it does automatic per DB tuning. So we talked about at the beginning how even though you have the super awesome query optimizer, you still have to tune it to your underlying database to get that last 20%. NEO can do that automatically, which we think is pretty cool. And our kind of headline result is that NEO is able to match or exceed the performance of a commercial query optimizer like SQL Server and Oracle within just 24 hours of training. So now obviously I need to justify that claim and tell you how the system works. So NEO looks like a classical reinforcement learning system with one small twist. The first thing that we do is we observe how a really basic query optimizer, like the one in SQLite, will handle a simple workload. So we start out by saying, okay, let's get some examples, some just an illustration basically of what a query plan kind of sort of looks like, so we can avoid totally catastrophic behavior. The second thing we do after that is we train a combination of a value model and a plan search module to emulate that expert. So before we do any actual query optimization, we're going to try to train our system to emulate that expert query optimizer. Then after that, we're going to create a feedback loop. And in this feedback loop, we're going to keep refining the value model using real query latencies that we actually observe from user submitted queries. So that's the high level of it. Next, we'll get into the details. So the first thing that we're going to talk about is how to represent query optimization as a reinforcement learning problem. And this comes down to representing it as a Markov decision process, which is a fancy term for basically a graph navigation problem. You have a graph, it has vertices, it has edges. At each vertex, you have to pick an edge, and your goal is to get to pick the best edges along the way. We designed NEO around 3 principles. The first is to find the right inductive bias, like I was just talking about. The second is learning from demonstration. The idea there is to look at an expert query optimizer ahead of time so that you start out with like an okay optimizer instead of starting out with something terrible. We're only going to do an overview of that today. Then the final design principle of NEO, which I won't have time to talk about, but you can feel free to see the paper if you're interested, is the idea of learned embeddings. And learned embedding is how NEO avoids things like histograms and exceptions lists and uses the learned model instead. So when we talk about query optimization as a Markov decision process, which is the first step in solving query optimization with reinforcement learning, we have to make a couple of assumptions in order to get the problem to fit. So for NEO, the assumptions that we made were that all query plan trees are strictly binary, meaning that every operator has exactly 2 children or is a leaf. Second, we only looked at non-distributed query plans. So like these aren't things like multi-node databases. There's no network partitioning. It's all happening on a single node. The third assumption we made is that there's a fixed number of join operators. And by fixed number of join operators, we don't mean like you can only have 5 joins. We mean there's a fixed number of ways to do joins. So for example, nested loop join, merge join, hash join, that's 3. So we're assuming you're not introducing or taking away query operators midstream. And the final assumption, which I know is a big one, is that every join is an equijoin. So like no fully advanced theta joins here, just pure this column equals that column joins. So again, I know these assumptions aren't totally realistic or representative of every database you might know of. These are just assumptions we made to try to get off the ground with reinforcement learning. So the idea behind modeling query optimization as an MDP is to think about it in terms of states and actions. So if I'm trying to optimize the relational algebra statement shown at the bottom here, a 5-way join between actors, appears in, film, produced, and company, I can think about an MDP that initially starts out in the state where nothing is joined at all. I've modeled every single relation as just R1 through R5, and then I have a set of actions available to me. These are things that I could potentially do to progress my query optimization. So for example, one of the things that I could do is I could choose to combine R1 and R2 with a hash join. And if I make this decision, I enter a new state. And in this new state, I renumber my relations. And now my R1 is this subtree, that is this hash join of actor and appears in. And my R2 is film and then produced and then company. Now my action space gets a little smaller, right? There are a few less options available to me, but I can continue to pick. So for example, next I could choose, okay, let's combine R2 and R3 with a merge join. So we do that, we renumber our relations, we get a new set of actions, etc. And we can continue this process until we end up with a complete query plan tree. Once we have this complete query plan tree, we can send it off to the execution engine, we can observe the latency that we get back, and now we know our reward. Now we know how good we did. So for any people who are MDP superfans, to just be precise with my terminology, in this MDP, every previous state, every state before the terminal state has a reward of 0. Once we hit that terminal state, that last state where no more actions are available, we execute the program and we record the latency. And then the reward is the negative latency. So by negative latency, I just mean reward is something you want to maximize and latency is something you want to minimize. So we just use the minus sign to make it go in the right direction.
So just to be clear on that, the reward is 0 in every step until the last one, which is minus latency?
Yes.
Okay.
Yep, so nothing, 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 nothing. You finish the whole query plan, now you get a reward. It's a perfectly valid MDP in this traditional sense, but yes, this fact that every previous state has a reward of 0 will be trouble later, yeah. So next I wanna talk about, so given that we've now defined the system as an MDP, I wanna give an intuitive overview of how deep reinforcement learning works in the context of a database system. So imagine that each one of those states that I showed you, each slide, is now one of these boxes. So my very first state that I have is just ABC, totally unjoined, just 3 relations that I haven't put together yet. From ABC, there's 3 possible choices I could make, right? First, represented by the top, I could join AB together, or represented by the second choice, I could join BC together, or the third choice, I could join AC together. There's other choices too, but I've omitted them so it fits on the slide. If, for example, I decided to merge A and B together first to join A and B, then after that, I could join C on the right, or I could join C on the left. And the red dots here represent the final latency that I would observe. So the red dots are not known at optimization time, right? Otherwise, we would just pick the best one, but they're the things we're trying to get through. So if you're using a traditional cost model, you're gonna have, and cardinality estimation method, you're gonna have some cost function C, which estimates like the intermediate cost of a plan, right? So your cost model might say, okay, before you join anything, just the raw scans that you're gonna have to do, that's gonna have a cost of 3. Then if you choose to do AB first, which is the top path, maybe that has an intermediary cost of 1. And then maybe the final join, when you join C on the right or C on the left, gives you a final cost of 5 or 6. Now, if your cost model is perfect, the cost of those last blue boxes will exactly match their latency. And that's the example we have here. So when you have a cost model like this, you have to do a big dynamic programming search to find the optimal query plan, right? So you have to expand 2 to the n nodes in order to find that query plan with latency 3. Now, deep reinforcement learning, on the other hand, instead of assuming a cost model, suppose we had a magical oracle function that we're gonna call Q, which maps each state inside of this MDP to the best possible latency we could possibly get from that state. So in other words, what our Q function does is it tells us, if I'm in this state and then I played the rest of the MDP exactly optimally, what's the latency that I would end up with? So the Q value of our first node is 3 because the best possible latency that I could achieve overall is 3. If I chose to go to the top node, joining AB first, then my Q value becomes 5 because now the best possible latency I can hope to achieve is 5. So just like we don't have the perfect cost model, we obviously don't have the perfect Q function either. But if we did, the search process would be really, really easy, right? If I had such a Q function, all I would have to do is look at all of the children of a particular state, say, hey, which one of you has the best Q value, the lowest Q value, and then I would pick that, right? And this search would be super simple, linear, or quadratic, because you have to expand each child. Would be very nice if we had it, but of course, obviously, we don't have such a Q function. But what we can do is we can learn an approximation of the Q function, which we'll call Q hat. And in general, this method of doing deep reinforcement learning, which is learning an approximation of that Q function, is called Q learning. And more generally, the approach of Q learning falls into a category of methods called value iteration. The idea with value iteration is that initially, we're going to have some totally random policy. We're going to navigate this graph by just choosing a random path through it, just totally random. Then, based on the paths that we see, we're going to train a Q network to predict, okay, when I see this node, predict this value, based on my experience from my initial random policy. Once we've trained that Q network, we're going to use that new Q network as our new learned policy. So now, instead of playing randomly, we're going to assume that our Q network, is exactly right, and we're going to play according to that. Then we're going to retrain the Q network and replay, and retrain the Q network and replay. So the differences between deep Q learning and a traditional database cost model is actually really, really small. The only difference is, instead of estimating the size of the intermediate value of every plan, you're instead estimating the best possible latency you could achieve from that intermediate plan. Very, very small change, but that very small change allows you to use a lot of deep reinforcement learning hardware. So the question then becomes, how do I approximate that Q function, right? How do I learn something that's going to tell me what the best achievable latency from any given state is? One thing that I could do is I could just take all that state information and I could arbitrarily flatten it into a vector, and then I could feed it into a fully connected neural network and hope for the best, right? And this sort of represents that deep learning mythos approach, right? This idea where I just treat it as a magical black box. But this isn't really how deep learning became successful, right? This isn't the specialized sort of neural network hardware that we're used to seeing. A second option is to try to find the right inductive bias and to build an intuitive network architecture. So this is really where the rubber hits the road. So what is the eyeball of query optimization, right? Eyeballs are good at recognizing objects. What's the thing that's good at recognizing query plans? Well, one possible answer to that question is that it's us, right? It's database researchers, database practitioners, people who spend their time looking at SQL queries and looking at database systems to try to decide what's going on. So we, based on that, we decided to try to figure out, okay, what's sort of the primitive thing? What's the deep down thing that people look for, humans look for when they're trying to decide if a query plan is good or not? So for example, with this query plan here, if you're a human being who knows a little bit about databases, you might see this query plan and you say, you have a whole bunch of stacked merge join operators, stacked sort operators. This might be avoiding a resort and might be giving you a very nice pipelined plan, right? Where you just do merge join after merge join after merge join. So that looks really good. I like that long chain of sort operators. However, if I instead showed someone this query plan and I said, okay, you're going to do a merge join and then a hash join and then a merge join and then a hash join, we as experts might look at that and say, okay, if you do a hash join and then a merge join and then a hash join and then a merge join, you're always going to have to do a rehash or a resort, right? And I don't know much about this database, but I know that's definitely going to be bad, right? Whenever I see a merge join on top of a hash join, that's bad news because the hash join output's not sorted, right? You might also know, if you have a little bit more familiarity with the underlying database, you might also know that the appears in relation is pre-sorted on disk. It's got a clustered index on it. And therefore, it should probably be going into a merge join instead of a hash join. So all of these little clues are things that we as human beings might use to try to figure out, okay, is this a good query plan or is this a bad query plan, right? And this is, of course, in addition to information about cardinality and estimates and all the other tools that we might use. So the question we asked is, how can we capture this sort of intuition in something compact that we can represent as a neural architecture? And the conclusion that we came to is that experts examine local structure first and then extract them into higher level features. So when I saw this plan, the first thing I saw was, okay, I've got one sort on top of a hash. That's not good. Ooh, there's another hash on top of a sort. That's not good. Ooh, and a sort on top of a hash. So first I saw the pairwise trouble, and then I saw the whole complete picture, right? Like, oh no, this is going to be just real nasty, right? So how can we make a neural network that is capable of learning those same kinds of patterns, capable of recognizing the same kind of trouble that might appear inside of a query plan that we as humans do? And the approach that we came up with is the idea of tree convolution. So like image convolution, if you're familiar, the metaphor will make sense. We're going to have something, our original data, which in this example is the plan tree on the left, which is a hash on top of a sort with A, B, and C. And then we're going to have a filter. And the filter is something that we're going to slide around the tree in order to create a new tree. And the way that it's going to work is like this. The first thing we're going to do is we're going to take our filter, represented by this thing in the middle, and we're going to line it up with the top of our tree into the top little triangle there. We're going to say, and then we're going to multiply or apply the filter to that particular node. So we're going to have ones for yeses and zeros for nos. So when we align this filter with this part of the tree, we say, okay, is the top node a hash join? Yes, it is. That's 1. Is the bottom left node a sort? Yes, it is. That's 2. And is the bottom right 0? No, it's not. So we're left with just 2. Then we take this, so we get a 2 as our new root node of our filtered tree.
So what the 0 symbolizes?
So the 0 symbolizes never look at this. I don't care what it is.
Okay. Okay.
So then we're going to take this filter and we're going to slide it down. And now we're going to say, okay, is this sort a hash? No, 0. Is A a sort? No, 0. Is B equal to 0? No, it's not, so 0. And then we're going to repeat this process for every node in the tree until we've completely rebuilt a new tree. So now we started with our original query execution plan tree, which was this hash on top of a sort, and we filtered it into a new tree where each value is a simple vector. In image processing terms, what we've just built is a feature detector. What this filter does is it causes in my new tree a really big number to show up whenever I see a hash on top of a sort. And it causes 0 to show up everywhere else. So what this filter does is it detects when I'm doing a hash join on top of a sort merge join. And it does that detection by causing the response tree, the tree on the right, to light up to become a big number whenever that occurs. And of course, you can imagine these filters for other things too, right? So if I knew that B was pre-filtered, was pre-sorted on disk, then I might know, okay, I want to know, is B being put into a sort merge join? And I can also have a filter that recognizes that, right? I can have a filter that sees, okay, is that B on the right and is that a sort on the top? And then my response tree again will light up when that pattern occurs and will not light up when that pattern doesn't occur. So just like an image convolution, I showed you some examples of some of these filters that were designed by hand, but in reality, these things are automatically learned, right? They're represented by parameters, and those parameters are differentiable, and we tune and change those parameters in order to build the actual filters. So it'll learn filters like these, but we haven't hard-coded this anywhere. We're still gonna learn those. The other trick is that, again, just like a convolutional neural network, we're gonna stack these, right? So one layer of tree convolution, one set of those filters can represent something like a hash on top of a sort, or B that goes into a sort, but it can't recognize like a long chain of hash sort, hash sort, hash sort. So in order to recognize those longer chains, we're going to apply more layers of tree convolution. And what applying more layers of tree convolution looks like is taking these response trees, these trees where I now have numbers instead of relational symbols, and feeding those again into another layer of tree convolution. So then I can have a filter that looks for a hash and then a sort and then another hash. And if I add another layer after that, I can look for hash, sort, dot, 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 right? An advantage of this approach, and I won't get into the details, is that it's really efficient to vectorize for the exact same reason that image convolution is easy to vectorize. Basically, each filter can be applied totally independently, which means that this stuff just soars on a GPU, which is an advantage if you've got a GPU around, and otherwise it's not super important. So going back to our original question, which is how do I approximate the Q value? How do I learn that Q function that tells me from this intermediate state, what's the best possible latency that I can learn? The way that we do that is with what we call a tree convolutional neural network. So we take a plan tree, a potential plan tree or partial plan tree. We feed it through 3 different layers of tree convolution. We do something called dynamic pooling, which is basically just a way to take the final set of trees and flatten them down into one vector. We do just two fully connected layers, and that's our cost prediction. So this is the value network architecture, the thing that we use to approximate the Q function. And we train this thing with standard supervised learning. We get, as we're playing query optimization, as we optimize more and more queries, we get more and more information. We train Neo assuming that all of our previous data was optimal, and then we have a Q.
So is it fair to say that that Neo will be as good as the master he's learning from?
That's a great question. Initially, no. So that's a pretty good lead-in. Man, you all are good at getting 5 slides ahead of me. I promise I will get back to that in just a second.
Right.
So a problem with which that question hints at is deep reinforcement learning is very sample inefficient. Sample inefficient means that you have to play the game for a really, really long time before you get good at playing the game. So in traditional value iteration, you start out with an initial random policy. You start out playing just totally randomly, right? And then you start learning your Q network from that. The problem with this is that in query optimization, doing worse takes longer. So this is a histogram for one of the join order benchmark queries. And it's a histogram of all of the different runtimes from one single SQL query. So for the same SQL query, we have some plans that take just 1 second. But we also have some plans that take like 6 or 7 months to execute. So unless you're willing to wait.
You actually wait 6 months to measure that?
Yeah, so there's a cutoff here. So like the histogram goes up to 1 year. I started this on a computer during my last year of my PhD. And after 6 months, we cut it off and we looked at how much progress it had made. And it was approximately 50%. And we just said, okay, it's a year.
Okay, fair.
We actually ran these.
You actually waited for months.
That's how I waited for months. Yes, I did a PhD. Yeah. Plenty of those. Yeah, so the moral here is that with the same query plan, if you play a random policy, you're very likely to hit one of these plans that takes between 10 hours and 4 days for this particular query. Now compare that to something like Pac-Man, right? If I'm playing Pac-Man and I die, if I'm really bad at Pac-Man, I'm gonna get my final score faster, right? Because I'm gonna fail and I'm gonna die and the game is gonna end. So for things like video games, deep reinforcement learning will work very, very well. But for query optimization, because doing worse takes longer, it's a huge problem. I'm not willing to wait 10 hours to 4 days to get a single training point, because in reality, you're going to need hundreds of these training points, maybe even thousands, before you start learning something good. So because of that, we had to figure out something to do. Luckily for us, heuristic query optimizers, just the super basic ones that you can find, for example, in the SystemR paper by Pat Sillinger, oh, that should say 79, not 89, work pretty well, right? Just a simple left deep join, the kind of stuff you would just transcribe from a textbook. So on this query plan, that's that green line. So it's not the fastest query plan in the world, not by far, right? There's some that take 1 second. But if we use just the heuristic optimizer, we get a plan that takes only about a minute or 2. Not bad, right? It's certainly better than 10 hours to 4 days. So the idea that we implemented with Neo is that instead of starting from a totally random policy, we'll use a simple heuristic system like the SystemR optimizer to bootstrap our policy. So to answer the question that was asked a minute ago, which is how quickly do we, where do we start out and where do we end up? The first experiment that we ran was we compared Neo against the Postgres optimizer. So in this experiment, what we did is we normalized all the latencies to 1. So that line that represents 1 there is the performance of Postgres. And then we used Postgres as a simple expert optimizer to bootstrap Neo. And when we did that, we got this performance curve. So initially we started out, even though we had trained on the Postgres expert on some different queries, we still started out 2 to 2.5 times worse than the expert. But quickly, within about 20 iterations, which represents about 18 real hours, we were able to outperform the Postgres expert by a reasonable margin, 15 to 25%. And we did tune the Postgres optimizer to try to, get the maximum performance that we could here. So to directly answer the question, no, it doesn't start out as good as the expert. It starts out a little worse because the queries that we used the expert to train on weren't exactly the same as the queries that we saw later. So there's like a generalization problem. But with enough training, we can eventually get there. We can eventually beat the Postgres optimizer.
Is there maybe you have it later as well? Is there like a rule of thumb or like some sort of list of observations as to why it is 15-20%? Maybe it's as what is a way to create better plans if you observe all the plans that you eventually came up with, which are 20% faster?
Do you mean like observed, like human, like what?
Right.
What is it? Oh, yeah. Mm-hmm.
Something to explain in English about why it's 20% faster, and maybe it's a rule of thumb that that it will be also intuitive.
Yes. So we did a basic analysis. Basically, what we did is we looked at what filters had the largest impact on the predicted latency. So on that first layer of the tree, we were saying, okay, which one of these filters matters the most? Which one, if I increase it by a little bit, will have the greatest response on latency? And that should be sort of a clue as to what is happening. And what we found was that the Postgres optimizer has 3 really big weaknesses. The first one is that its cardinality estimator consistently underestimates, especially larger joins. And as a result, it will often pick to use a nested loop join instead of a hash join or a merge join. We're not the first ones to observe this. I think Victor Lies's paper had this note in it as well. If you simply take Postgres and you turn off nested loop join, 5% boost right there. And so we confirmed that Neo was able to learn that Postgres was using that infrastructure too much. The second problem that Postgres had, so when we ran these experiments, the current version of Postgres was Postgres 10. We're now on version 13. Postgres 10 had a bug in it where its query optimizer would often not use a hash join because it wouldn't look at how much working memory was actually available on the machine. It would assume a default amount. So it would assume, oh, I only have 8 megabytes of working memory in order to perform this hash join. So if it thought the left side, build side of my hash join doesn't fit within 8 megabytes, I can't do it. I have to do something else. It'll spill. It turns out this was a simple bug, and it's one that came to light very, very quickly when we started examining the query processes that this was looking at. So we sent this off to the enterprise DB people. Postgres 11, it's fixed, which is good news and bad news. It's good news because it means like everyone's Postgres is faster, and it's bad news because it means if you did this plot today, it would be 2% less, 2% less good for us. But the final thing, and the one that's not such an easy fix, is that Postgres was not able to learn the complex correlations that are underlying this data set. So again, this is that IMDb data set. One of the things that our model was able to learn was that there is a very, very strong correlation consistently overestimated by Postgres between the actors table and the movies table. So intuitively what's happening here is there are some actors that are in like so many movies, but the vast majority of actors, like 90% of them, are in like one movie. Like they have one credit at all. So what Postgres does is Postgres looks at that histogram and says, oh, 90% of the actors are only in like one movie, right? So when it estimates the size of how many actors are in this movie, it uses the value 1, the standard uniformity assumption. But the average query, the average question that's asked of the IMDb database isn't about those 90%, right? It's about those heavy hitters. More people are searching for Tom Cruise than are searching for some actor that appeared in one movie, right? So as a result, Neo was able to learn a filter that said, okay, am I looking at one of these famous actors? Am I looking at one of these actors that is consistently underrepresented by the Postgres estimate? And if so, change my join ordering. So that's like a data-specific fact that Neo was able to learn. So when we talk about Neo tuning itself to the underlying database automatically, that's one of the examples we usually give.
That's very interesting. Do you think that one could say, for example, as one potential observation, that if we go to the original optimizer of Postgres, or some other optimizer, of course, right? And we really make sure, because this is kind of the opposite of what you said in the beginning, but I want to ask again, and you really make sure that the correlation between columns is very well captured. Would that make existing optimizers much better, and maybe as good as it gets, or this is not all?
So that's not. So those were three things that, if fixed, bring this curve up a lot. But Neo still does about 10% better, even if you fix all three of those things in the original Postgres optimizer. Some of those things are kind of unintuitive or a little strange. So like, for example, Neo picks merge join way more often than Postgres does, and it does it in situations where we were surprised to see that the merge join latency was better. We're not entirely sure what's happening there yet. We're still investigating it. But yeah, I think there is a lot. So to directly answer the question, there are some things like underestimating cardinalities and using loop joins too much, or underestimating particular operator types like the hash join, right? Those kind of things, yeah, we should get in there. We should fix them if we can. They're hard bugs to solve, but they're bugs, right? The third thing, the correlations between tables, it's much harder to capture. Now, if you're a DBA and you're working on one particular database, like not a whole DBMS, but one particular database, then yeah, you can note where those correlations are because you know about them semantically, and you're going to do better. You're going to blow Neo out of the water, right? If you have a human being as your query optimizer, A+, right? If you can pay someone $100,000 a year to sit at a desk and make all of your query plans perfect, no reinforcement learning system is going to beat that. What we're trying to do is figuring out, like, for people who don't have a DBA, which is like 95% of all databases, how can we learn these things automatically, or how can we understand them in some way that's sort of hands-off, hands-free. But yeah, you're absolutely right. Human beings can totally sit down and beat the pants off all these optimizers.
That makes sense. That makes sense. Thank you, Ryan. There's a question from Harsal. Harsal, you want to go ahead and ask your question?
Yeah. Hey, so if I understood your model correctly, if you just use reinforcement learning to choose actions, then you will have the issue with delayed rewards, because you don't know until the entire action is, entire sequence of actions executed. So if I understand this part correctly, you choose an action which modifies your entire query tree, and then you use this tree convolution network to predict the cost of the entire tree. And then you feed back that cost to the action.
Correct.
So that's your way to bypass this delayed rewards issue, I guess. Yep,
exactly.
Okay, perfect.
And
Thanks
so
for the clarification.
That's actually not our contribution. I should be clear, that came from the Nature deep Q learning paper. They also had non-sparse rewards. They also had interstate rewards, but they also talked about how to backpropagate those final rewards to the original actions, and we used the same technique. So yes, okay. You're exactly right, but just to be clear, that's not ours. Yeah.
Okay, thank you.
So a common complaint that we get when we walk this work around is that the Postgres optimizer sucks. A lot of people say it's not nearly as good as the state-of-the-art optimizers. It's not nearly as good as what we have in SQL Server or Oracle. So the next thing that we compared against was those state-of-the-art optimizers. So here we're looking at the Oracle DBMS. The black line at 1 represents the performance of Oracle, so it's normalized there. This green line represents the performance of the Postgres optimizer on the Oracle system. That means that you use the Postgres optimizer, you get a query plan, but then you execute it on the Oracle engine. And so approximately, if you use the Postgres optimizer, you get plans that are 70% slower, 70% worse than the Oracle optimizer. Now, for this experiment, we use the Postgres open source optimizer as our expert. So we started training at that sort of 1.7 mark. And this is the learning curve that we ended up with. So you'll notice that we were beating Postgres by around iteration 20. It takes around iteration 40 in order for us to catch up with Oracle. That represents about 24 to 30 hours of training in time-wise. So we see the exact same pattern. We see initially we perform pretty badly, 2.5 times, and ooh, that's really bad. So that actually starts at 3.5, but I'm being a bad scientist and I cut off the y-axis. Sorry about that. But yes, that starts at 3.5. Then it quickly descends surpasses the original optimizers that it was trained on, and then hits that one line where it starts to outperform the Oracle optimizer. And by iteration 100, 100% of the queries are faster than the Oracle system. So this was a big surprise to us. We were sort of expecting for Neo to kind of match the performance or even be a little worse because these commercial systems are so much better than the Postgres system. But yeah, we can actually find improvements in certain places as well. Again, this is on the join order benchmark, which is very difficult in terms of query optimization. We have experiments in the paper where we run TPCDS. On TPCDS, we do not beat the performance of Oracle or SQL Server, but we come within 2 to 3% of it. Our hypothesis there is like TPCDS is what those 45 to 55 full-time employees at Oracle are using, what they're optimizing against, right? So it's kind of cool that Neo all on its own can come up with an optimizer that's only a little bit worse than all of those experts, right? It's neat, but of course, at the end of the day, the human experts will win. So the last thing that I want to talk about is the tail performance. Like how does Neo perform on like worst case, best case, and that kind of thing. And I also want to highlight a very interesting feature of Neo, which is that the cost function is modular. So before, in all the previous experiments, we were training Neo to minimize latency, just overall. It's the cost that it was trying to decrease was just the query latency. We call that the workload cost. Another thing that you can do is you can train Neo to minimize the ratio of its query performance versus Postgres query performance. So say you have some baseline, like, oh, this query should be this fast. You can tell Neo, hey, I want you to perform relatively better than this particular optimizer, and I'm going to heavily penalize you if you perform worse. So what this graph is showing is the difference between the query plan that Neo found with these two different cost functions for each of the different join order benchmark queries, sorted by the biggest difference. So the x-axis is interesting if you're familiar with the join order benchmark, but if you're not, you can essentially ignore it. And so what this is showing is when we use the workload cost, we can get huge gains on some queries. So for query 16b, the very first query on the far left, we can beat Postgres by almost 45 seconds. That's huge. That's awesome, right? But using the workload cost in the worst case, 24a, the far right side of the x-axis, we're actually doing worse than Postgres by almost 11 seconds on query 24a. Now, if I change the cost function to instead of saying minimize latency overall, instead I say just try to beat Postgres, and I'm going to heavily penalize you when you don't beat Postgres, we get a totally different performance. We get the green bars. So when we change the cost function to this, on 16b, we only get a 12-second gain. Way less good than the 45 seconds we were getting before. But a lot of our regressions, a lot of those tail latency increases are totally erased because now Neo is more conservative, right? We've told it your goal is to beat Postgres. Your goal isn't to minimize query latency. So on queries like 24a and 18b at the end, we actually start seeing small improvements instead of those decreases. So of course, the actual function that you want to use is going to depend a lot upon your actual workload. If in your actual workload, you have some queries that you care about a lot and some queries that you don't care about at all, you can actually encode that into the cost function, and Neo will automatically learn and try to optimize that. If you're a cloud provider and you don't necessarily care about, for example, your users and query latency, but you care about their I/O operations, you care about how often they're hitting the disk, you can tell Neo to optimize for that. So it creates a very flexible framework, whereas if you wanted to take a traditional query optimizer and change its optimization metric, you'd have to come up with a whole new cost model, right? With reinforcement learning, all you need is a way to measure it, and you send it back as information to the system. So yeah, that's that experiment. The conclusions, and I want to be generous here. We do think Neo is the first learned end-to-end query optimizer. We have demonstrated that it achieves performance on par with these commercial systems, but there are a lot of limitations, and I want to talk about those in depth for a little bit. So the first one is this dependency on an expert, right? We need to use the Postgres query optimizer in order to get off the ground. If we don't use the Postgres query optimizer to get off the ground, or a simple system R style optimizer, instead of starting out 2.5 times worse, we start out 100x worse, 1000x worse. We hit those catastrophic plans, those ones that take months. So that dependency is an issue because you basically still have to maintain some kind of query optimizer. It doesn't have to be perfect. It doesn't have to be very good. It can be as simple as one transcribed from a textbook, but it's still work that you have to do. The second major limitation of Neo is that it assumes a fixed schema. And this is a huge deal breaker for practical applications, right? If you add a column, drop a column, new table, remove a table is actually okay. But add column, drop column, new table, any of those kind of schema language, DDL stuff, you got to retrain the model, right? When we featureize those.
One quick question. If you train your model with, for example, only left deep plans, right? Are you going to get other plans eventually? I guess yes, but I just want to verify.
Yeah, your intuition is right. So this was one of the experiments we did that's in the extended version of the paper. So what we did is we trained on a left deep only optimizer, and then we plotted over time the number of non-left deep trees that Neo used as it progressed. And initially, in the first 5 or 6 iterations, it uses almost 100% left deep trees. And then it slowly starts incrementally adding small modifications until in the end it converges. So we plot the training starting from system R versus starting from Postgres, and then we plot the percentage of non-left deep trees. And after about 50 or 60 iterations, it converges, meaning they have learned similar or they've learned to pick bushy trees approximately an equal amount of time. Now, 60 iterations, it's like 3 days. So, you know, grain of salt there. So the expert has an impact on the initial performance of the system. That impact does go away after a lot of training. But because of the fixed schema restriction, you might be doing that, you might be restarting that training a lot, right? Like if you were modifying your schema every 3 days, suddenly your expert matters a whole lot more, right?
Right. Also, does it make sense to parallelly run some part of training and execution? Not the very. Maybe you can do training of 1 day and then start operating and keep training for another day.
Yeah. That's totally because Neo, one of the advantages of a value iteration model is that it can work off policy. And what off policy means is that if someone else is playing, you can still learn from watching them. So one possible instance of the Neo system could be you watch some query optimizer go for like a day. And then once once a human operator says, oh, okay, Neo's finally learned something that's good, you switch it over, right? And then at some point, if you need to fall back, you can just switch back. We didn't investigate that directly, but it's definitely a model we're like thinking about. It has disadvantages too, because you got to find all that extra compute, right? To do the training offline. But yeah, it's definitely a possibility. The final major limitation is concurrent queries. So Neo requires a reward signal, right? Like you have to say, this was the latency of this query. And Neo assumes, because of Q-learning, that latency is purely a product of the actions that Neo took. So Neo assembles a query plan tree, it ships it off. It's expecting that same set of actions to produce that same latency more or less every time, modulus invariance. Concurrent queries blow this assumption up, right? Because if I'm running query A with query B, they might cooperate, they might share. I might actually get a super linear speed up by running those 2 queries at the same time. But if I run query A with query C, it could slow down a ton, right? They could compete for resources, they could lock up the disk, it could be a disaster. So that's also like a major limitation. But again, we're not saying that Neo is like some system you should put into, you should deploy tomorrow. We're saying we think it's an interesting first step. So now to circle all the way back around to the original multi-arm bandit comment, a new thing that we're working on, which will hopefully be coming out soonish, we're not sure where, maybe probably an archive first, is a new system that we're calling BOW, which is the bandit optimizer. The idea is that while current optimizers might not be good at picking the best plan, they are very, very good at avoiding terrible plans. So the idea is, can I take a query optimizer and ask that query optimizer and say, give me your top 1,000 plans. Give me the best set of plans that you think might feasibly be okay to process this query. And then I can treat each one of those plans as an arm in a multi-arm bandit problem and try to multiplex them together. Try to, for a particular query, figure out which one of those query plans is going to be good. This has some benefits in that we never hit, if your query optimizer is good, you're never going to hit that 2.5x terribleness. But it requires your query optimizer to be a little more sophisticated. So we have one preliminary result for this. So this is on a 100,000 query workload, again, over the IMDb data. On the x-axis, we have the time, and on the y-axis, we have the number of queries finished. And the idea is you just execute as many queries as you possibly can, as fast as you can, and we plot the resulting curve. So after about, so here we show BOW, Postgres, and Neo. BOW, using this bandit approach, has a much better slope almost from the get-go. After just about an hour, its slope is better than Postgres. And it continues on. But because BOW is limited, because it doesn't have that full range of action that Neo has, after 60, 65 hours or so, Neo catches up with it. So advantages and disadvantages to that multi-arm bandit approach. Advantages are you train way faster, you get going way faster, you can handle changes way quicker. The downsides are you have many fewer degrees of freedom. So yeah, that's all. You can find these slides online at that URL. You can follow me on Twitter if you want to. I'm not in this current job cycle, possibly thankfully, but I will be looking for the next one. This is the last year of my postdoc. So, let me know.
So let's everybody thank the speaker. Maybe you can unmute and clap with me to imitate the real feeling from the actual seminar room. So thank you very much. Guys, is there any other questions? You can grab a mic and ask a question if you have one.
I have one.
Yeah.
So you are using value iteration over here, and then you are using the sum optimizer as a bootstrap for starting to initially give, not have to learn from a completely random state. I was wondering if you have looked into policy optimization, like policy iteration, because some of them provide monotonic improvement guarantees. And is it possible to let go of this bootstrapping step if you start with policy optimization? Because it should be able to monotonically always improve the performance and get on with learning actual stuff quite fast.
That is a great question. So the rejoin system, the system that's a predecessor to Neo, uses policy iteration-based methods. For those of you that are unaware, value iteration methods work with this Q function thing. They take in a potential state and they predict how well am I going to do. Policy iteration methods, on the other hand, use the network as the policy itself. So the policy takes in a state and produces an action. So the difference is the Q network tells you how good a state might be. The policy network says, what action should I take? And when you have a policy network, there's some very, very clever algorithms like TRPO and PPO and monotonic search that can allow you to incrementally improve your policy with a lot of very smart, still stochastic, but very smart error guarantees. The issue with those, especially the monotonic ones, is that the monotonic improvement only works from the point of view of the neural network. So you would need some way to train your policy network to your differentiable policy network to first be as good as your query optimizer, and then those monotonic policies would all work. But unfortunately, because the Postgres optimizer is not differentiable, you can't. It's easier said than done. But yeah, you're totally right. That's it's a very, very interesting area. We're just not entirely sure how to do that first step where you make the neural network good enough to start the monotonic increase.
Okay, thank you.
Great. Any other questions?